Okay, so what we're going to do now is we're going to solve the problem of elevation of water at the interface of three materials. And so the problem looks a little like this. We have some aquifer, and the aquifer is confined. And this is important to understand, that the assumption is that the water table is above the top of the aquifer. So here, make little dots here, and so this is our aquifer. And I'm using these sort of little hashy lines here, and that's going to be the confining layer. And then on the water level is going to be above the top of this aquifer, and that makes it confined. So there's two things that make a confined aquifer. One is that you've got this confining layer, which is, in this case, let's say it's clay, and so the material is physically less permeable above the aquifer. And then the other thing is that it's charged. It's got water pressure on top of it. And then on the other side, we've got water over here. And we are going to look at an aquifer with three different types of materials. So this material over here, we're going to say that this is clay. And that's not typically an aquifer, but we're going to be interested in seeing how energy drops through different materials. And this is really important because as civil engineers, what we can do is we can manipulate energy based on the type of material. And it's a little complicated because you're going to say, well, how do we determine what's what? But we're going to make these sort of simplifying assumptions just to kind of understand how energy drops through different materials. And then this material over here is going to be silt, and this is going to be sand. Okay. And so for this example, our aquifer is going to be 50 feet tall, and it's going to be 1,000 feet wide. And we've got water that's flowing through here, and we want to know kind of how that water, how the energy of the water is dissipating as it's going through. Is it going to be a straight line? Is it going to dissipate more through one material than another? And so for our example, and sometimes it's easier, when we put numbers on things, that this is going to be 100 feet. So what we have here is that we've got 100 feet from the bottom of the aquifer to this water level over here, and then we're going to say that this is 80 feet over here. And then the question is, let's say that this is going to be material 1, this is going to be material 2, and this is going to be material 3. So essentially we want to know what the elevation of the water is at the interface between 1 and 2 is, and we want to know what the interface between 2 and 3 is. So we want to know what this one is and that one is over there. And for this problem, the total distance is going to be 1,000 feet. And this distance here, we'll say that that's 333 feet, that's 333 feet, and this is 334 feet. And so the total distance is adding up to 1,000 feet. And we're going to do that just because it's going to be, we're going to solve this numerically later on using a computer program, and we're just going to try to solve the same problem. Okay, so now we have to determine what the material properties are. And so for the clay, a typical permeability of clay is 1 times 10 to the minus 7 centimeters per second. For silt, a typical K is around 1 times 10 to the minus 5 centimeters per second. And for sand, it's 1 times 10 to the minus 2 centimeters per second. So now we've got three different material properties. We've got three different lengths. And then we are going to try to figure out what these elevations are at those 2 points. And so how do you solve this problem? And so in order to solve this problem, we're going to use three ideas. First off, we're going to use continuity. So what is continuity? Flow in is equal to flow out. So we're going to say that the total flow, Q, and let me just write this like this. Hold on a second. This is going to be the total flow, Q, and that's going to be equal to Q1, which is equal to Q2, which is equal to Q3. So Q3 is the flow through 3, Q2 is the flow through 2, Q1 is the total flow through 1, and the overall flow through this whole system is going to be the same thing. Flow in is equal to flow out. So that's our first concept. So this is continuity. Okay. The second idea that we're going to use is energy drop. So we're going to say that the total energy drop is going to be equal to the energy drop through 1 plus the energy drop through 2 plus the energy drop through 3. So when we're looking at this difference between here and here, that's going to be H1, H2, H3. And we can really kind of get hung up with all the symbology and so forth, but really we're just trying to understand this basic idea. So this is energy. Okay, now we have one more concept that we're going to use, and this is constitutive. So what is constitutive? It means that this is a property that defines the material. And so in order to use constitutive, we're going to use Darcy's law. So Q is equal to KIA. And remember, that's negative. Of course, it'll be applied equally to each one of them, so it doesn't really matter. So this is the constitutive relationship, and we're going to put all this stuff together in order to understand what's going on. Now remember, this is our permeability, and this is our gradient, and this is our area. Okay, and so we've got 1, 2, 3 equations, and using these 3 equations, we can solve for what the energy is over at the interface between 2 and 3, and the interfaces between 1 and 2. So how do we go about doing this? Well, the easiest way to do this is to try to put everything in terms of the same variable. So let's put everything, let's say, in terms of H2. And so let's look at this constitutive relationship. So your constitutive relationship is negative K multiplied by the gradient multiplied by A. Well, what is a gradient? Well, it's the change in elevation over the length. So we're going to look at what is, and we can also multiply it by the area. So what is the change in elevation going from one side to another? Okay, so that's the general constitutive relationship. And so we could say, okay, well, Q1 is going to be equal to K1, negative K1, negative delta H1 divided by L1 multiplied by area 1. Okay, and then Q2 is equal to negative K2, and I forgot to write that 1 over there, multiplied by, I got a little over rambunctious with my negatives there, and so this is negative H2 multiplied by L2 multiplied by A2, and then Q3 is equal to negative K3 delta H3 multiplied by L3. And so in this case, this is L1, this is L2, and this is L3. So those are the different lengths. And we know what the let's say in this case we know what the permeability is for each of these, and we know what the length is. Okay, the only thing that we don't know really is those head drops. So if we can figure out what the head drops, then we have solved the problem. So first off, we start with these constitutive relationships, and then we're going to substitute in the idea of continuity. So remember that Q is equal to Q1, which is equal to Q2, which is equal to Q3. So we can write everything in terms of each other. And so let's say that we want to write, ultimately we're going to try to write everything in terms of H2. So we're going to just say that negative K delta H1 over L1 multiplied by area 1 is equal to negative K2 delta H2 divided by L2 multiplied by area 2. Okay, so the area for all these are going to be the same. So those just cancel out. And then both of those are negative, so that'll both be positive. And so now we can say that delta H1 is going to be equal to that L1 divided by L2 multiplied by K2 over K1 multiplied by this delta H2. Okay. And then we could do the same thing for the third. So we know that K2 multiplied by delta H2 divided by L2 multiplied by A2, and that's all negative, remember, is going to be equal to negative K3 multiplied by delta H3 divided by L3 multiplied by A3. Okay, so again, the areas between these are all the same, right? Because we've got the same height over here, so this area is going to be the same going through for each one of those, so that can cancel out. The negatives definitely can cancel out, no problem there. Okay, and we want to write everything in terms of K2, or delta H2, and so we could say, well, delta H3 is going to be equal to delta H2, and then we've got K2 divided by K3, and then we've got L3 divided by L2. And so now we've written this in terms of delta H3 and delta H1. Okay, so now we're ready to substitute the energy equation. So remember the energy equation, so the total head, I wrote a little delta there, is going to be equal to that delta H1 plus delta H2 plus delta H3. Okay, well we know what delta H1 is in terms of delta H2, and we know what delta H3 is in terms of delta H2. So now we can substitute those things that we substituted or we solved for before. So that total head is going to be equal to that K2 over K1. So we're just writing this over here, we're just writing it down, multiplied by L1 over L2, and that is going to be multiplied by delta H2. Okay, plus delta H2, which is going to be the same thing, plus this one over here, delta H3. Well, delta H3 is just delta H2 multiplied by K2 over K3, L3 divided by L2. Okay, so now we've got everything in terms of H2 and delta H. So for this problem, we're going to assume that we know what the elevation is at these two boundary points. So we know what this elevation is, and we know what that elevation is, and we're trying to figure out what the elevations are at those intermediary spots. Because really what we're trying to figure out is how does energy dissipate through different types of material over these different lengths. Okay, and so we know what the delta H is, and so we can solve for delta H2. So we could just say, well, okay, delta H2 is going to be equal to delta H divided by K2 over K1 multiplied by L1 over L2 plus 1, and then we've got K2 over K3 multiplied by L3 over L2. Okay, so now we can figure out what that head drop is in 2, and then once we know what that head drop is in 2, then we can very easily figure out what the head drop is in 3, and we can also figure out what the head drop is in 1. So this problem is almost solved. Okay, so now let's look at our problem. So for this problem, that total head drop is going to be what? It's going to be this elevation minus that elevation, or 20 feet. Okay, so our total head drop is going to be 20 feet. Now, K2 is silt. So the properties of silt are 10 to the minus 5 centimeters per second. And all the units are the same, so I'm not going to worry about unit conversions. Now, K1 for this problem, that's going to be the permeability of clay. So that's 10 to the minus 7. L1 and L2 are the same, so that's just going to be 1 plus 1. And then we've got K2. K2 is just 10 to the minus 5th. And then we've got K3, which is going to be 10 to the minus 2. Okay. And so what's going on here? Well, this is delta H2. And so delta H2 is going to be 20. And so this is negative 5 divided by 10 to the minus 7. And essentially what that's going to be is this is 2 orders of magnitude difference. And so that's going to be 100. This is 1. And then we've got 10 to the minus 5 divided by 10 to the minus 2. And so the difference between those two is 3 orders of magnitude. So that's 10 to the minus 3. So what does this mean? That means that we've got 20 divided by essentially 100. But we'll say that this is going to be 101. And so the drop is going to be about 0.2 feet. So there's out of those 20 feet, only about 0.2 is being dropped through that middle layer. So now we can solve for those other 2 drops. So that delta H1, and I'm gonna scroll back over here. So this is the equation here for delta H1. Okay, and that's K2 over K1. And then going back here, L1 over L2 multiplied by delta H2. So we know delta H2, that's at 0.2. And so K2, remember that's our silt. So that's 10 to the minus 5. And then K1, that's our clay, which is 10 to the minus 7. L1 and L2 are the same, so that's 1. And then that's 0.2. Okay. Well then that's going to be essentially 100 multiplied by 0.2, or about 20 feet. And we've got a little bit of difference in the rounding here, and if we go through this very carefully, we'll see that this is not 0.01, but it's going to be slightly more than that. And so this is going to be, this drop over here is going to be a little bit more than that, okay? Which doesn't make complete sense, but essentially what we're looking at here is that the total drop, most of the drop is through H1. Now what is the drop through H3? And you probably have the hang of this at this point, but I kind of like to go through and just look at the numbers here. So this is going to be equal to K2 over K3. And then our lengths over here, and they're both going to cancel out, but it's going to be equal to L3 over L2. And that's all multiplied by delta H2. So K2 is 10 to the minus 5, that's our silt. K3, that's 10 to the minus 2, which is our sand. These two are 1, and then we're multiplying this by 0.2, and so the drop over here is going to be 0.2 divided by 1,000, very small. So essentially, if we had to look at this, we would say, okay, well, we've got 3 materials. Okay. We start out over here at 100. Our delta H2, or I'm sorry, just number, this is 3, this is 2, this is 1. So that delta H3 is very small, so this is going to be about 100. Okay. Then going from 2 over here, we've got a drop of about 0.2, so we are looking at about 99.8 feet right here, and then we'll drop the remainder over here, and this will take us over to 80 feet. So we took our H over here, and we subtracted about 0, and then we subtracted 0.2, and then we subtracted the remainder, which in this case will be 19.8 feet. Okay. Now taking a step back from this, what have we learned? Well, we've learned that the permeability is very important in terms of energy drop. And so if you're trying to drop energy, you're not dropping any energy, any significant amount of energy in these more permeable materials. But that clay material over here is permitting you to drop all of this energy through that material. So as you're looking at designs, you might want to drop energy. You want to control how energy is moving through soils, and one way to do that is to use clay. That will help you with your various designs. And this is used through modern earth dam design, and so it's important to understand how that energy is dropped through. This is a simple example, but you can use it for more complicated things as well.